Taisija Kozarina will present Unlocking the Power of Python and PyTorch for Biomedical Image Segmentation.
Hi everyone. Is the sound okay for everyone? Okay, good. So it's really nice to see so many people here. It will be my first time speaking at the IT conference, so don't be harsh on me. Yeah, my name is Taisija. I work as a data engineer in Accenture Baltics. And I have an exciting topic to share with you. It's unlocking the power of Python and PyTorch for biomedical image segmentation. So let's jump into it. If you haven't met each other already, let me introduce you. PyTorch is a machine learning framework, or technically it's a library for Python. It was released in 2016, and it covers many use cases such as natural language processing, computer vision, audio text processing, etc. And it also provides tools for almost the full machine learning pipeline from data preprocessing to model deployment. And actually, a year ago, I was working on a project where I needed to create a custom semantic segmentation model for biomedical imaging, and I decided to go with PyTorch. So today, I would like to share with you the use case I had and the lessons I learned on the way. So from the title, you can kind of say it was a research paper more than a development project, and it took me 2 business days to remember it by heart, so bear with me. The title is CNN-based pipeline-related artifact and damage recognition in immunohistochemical staining scans as preprocessing step for pathological analysis. So thanks. Thanks. I know it's complex, so I suggest. Thank you. So yeah, I suggest let's break it down quickly. So we start with the subject area of this work. And subject area is actually pathology and pathological analysis. Unfortunately, it's a widely used, widely known word. Pathology is a field of science that deals with diseases and their natural life cycles and all that is related to diseases. This includes such important tasks such as cancer research and biomedical analysis. But actually, before the pathologists get their data, the data undergoes a certain pipeline. And this is what immunohistochemistry does, steps 1, 2, 3. So first, data is manually collected. In most cases, it's a biopsy, so a super small tissue sample. Then it goes under chemical processing to reveal several chemical markers. Then it is scanned under special multi-wavelength scanners, and only then it is passed to the pathological analysis. So you can imagine we have so many stages. We also have a lot of possibility for errors occurring at any stage of this pipeline. And you see the errors introduce different damages and artifacts. They're all different. And we actually, if we let the damaged data and artifact data participate in the pathological analysis, it will distort the results and propagate the error further. So naturally, we need to exclude the artifacts somehow from the pathological data. How it is done currently is pathologists, real people, sit and they have this software which is really similar to Microsoft Paint, where they basically select, like draw around circles that needs to be excluded. And this is bad for majority, for many reasons. First of all, this is time. Second of all, this is cost. And third of all, they introduce their own errors on the way. So yeah, meet the artifacts. There are 9 classes of artifacts. They're kind of similar, kind of different. How I know that there are 9 classes of artifacts is that I consulted actually with the industry specialists and we defined some classes, but then I also adapted it for the computer vision tasks. This is, for example, the reason for having class 2 and class 8 as separate, but logically they're the same. Yep. And this is the input data I used. So on the left side, you see the scanned image, and on the right side, you see corresponding binary segmentation mask. And the areas which we are interested in are in the white color. So layered on top of each other, they look something like this. And in the classical case of computer vision, this is what you want to see as the model output. So a mask that somehow colors the areas that you're interested in. And in our case, we also have another layer of complexity, which is we need to know for each segment which class it belongs to. So something like this. Now we know what the problem is, so we can move to the fun part, how to do it with, how to solve it with Python and PyTorch. First of all, you need to define your data. In statistics and in most machine learning computer vision tasks, we work with matrices, and in PyTorch, matrices are called tensors. It's essentially the same thing, so a matrix of any dimensionality, but on top of that, you have cool stuff like gradient tracking. So this is, imagine your matrix has itself the data, and also it has a history of all the operations applied to it. This is really useful when you do backpropagation because you can do it many times faster. On top of that, PyTorch also provides great support for GPU usage. So at any time you can choose where your data is stored and processed with one line of code. And also, if anyone is familiar with the relational databases, SQL and stuff like that, you know the concept of views. So PyTorch actually has the same for tensors. Also cool in several tasks. Once you have your data lives in a dataset, in a collection. For that, PyTorch offers a dataset primitive, and you only need to define two methods. One is len, which returns length, and the second one is getItem, which returns a single sample for your dataset. So in my case, it was super cool to have that flexibility of defining what do I get as sample, because I also needed an adequate amount of preprocessing done at this place. I'll show you a bit later what kind of preprocessing I did, but in the meantime, it's important to understand that you have the flexibility. For example, I did in my case, one sample was represented by two images, so I had the flexibility to do that. It's also great for multimodal data when you have not only image, but something else, for example, text. Yeah, and once you have your dataset ready, the engine that will feed it into the training loop is actually data loader. This is also great because you only define hyperparameters. The code snippet you see on the slide is actually almost all you need to do. And underneath, the data loader class takes care of the shuffling, batching, multiprocessing, stuff like that. Yeah. And you actually can go a step further and simplify your life with just one library, Torch Vision. This is a library specifically for computer vision. It has a lot of utility methods. It also has ready-to-use datasets and models. So yeah, and as promised, this is the preprocessing I did. So spoiler alert, I will use two architectures and compare them. So I needed two distinct formats, and all of this was done using PyTorch. But this is also a good point to admit that I did use other libraries as well, for example, OpenCV. And this is also great because you have the flexibility of not just sticking to PyTorch, you can integrate it with other libraries as well. The only thing you need to take care of is format, because if anyone worked with OpenCV, it works with NumPy arrays, but PyTorch sticks to its native tensors. So just the formats transfer back and forth, and you're done. So yeah, we have our data sort of ready, but there's a catch. So for any seasoned machine learning engineers, developers, you might have been able to catch that already. I showed you a binary mask, which is a binary mask, right? It's 1 or 0. There is an artifact or there isn't. But I also showed you a slide with 9 classes. So how does this work? How do we turn a classless problem into classification problem? We somehow need to do that conversion. But good news is that we have options. Option number 1 is to go and relabel the data manually, which would probably take me another year or so. And option number 2, the red pill, is using unsupervised learning, in other words, clustering. Guess which one I used. Imagine I said the blue one, that's done. Yeah. But no, I used the unsupervised learning, and we implemented clustering here. So take a look at this selection of the artifacts. They kind of look similar, some of them are different, but our human eye, is actually really good at catching the similarities and the pattern recognition, because this is how we survived for many billions of years. So clustering algorithm is actually based on how our vision works. So first of all, what we do, you can trail your logic here. You look at the samples and you see the features that make them distinct. For example, the color, the size, the form, some of them are like blurry or something, and you group them logically somehow like that. So they're more similar. It makes sense already. But then the second step, and actually the last step, is where you draw the borders of the clusters. And this majorly depends on the algorithm you choose. There are many. For example, in my case, I tried many, but I ended up using k-means, which is very classic. So it takes a random point as a center, and then it assigns samples to it iteratively. That's it. You have your clusters. And actually, I didn't code this myself. This is a known fact that there exists a Python library for anything you want to do. So this is the case. I found this library. This is a really good library. It is Python, pure Python, no PyTorch here, and it does exactly what I said. But actually, preparing for this presentation, I took a quick Google search and revealed that there are many PyTorch native libraries now that you can use. So feel free to explore. But yeah, there's one small note that you have to consider. These four samples, under certain circumstances, our human eye would actually group them in one group if we had 1,000 of them, let's say. So you can never expect 100 accuracy from an unsupervised learning algorithm, unfortunately. There's a portion of manual post-processing you have to do after you consider your algorithm is done. So this is just one thing to keep in mind. You cannot rely on it on 100%. Yep. And once we have the labels ready, we can move to the segmentation model. So let's get the terminology straight. I feel like in computer vision society, a community, we often have this terminology wars. One thing means one for one person, something completely different for another. So semantic segmentation is a type of task where you want to classify a pixel on an image to one or more classes. Right. So this is top right example. Okay. Yeah, and for semantic segmentation, there are options that you can follow. Sorry. Yep. I use two architectures to try and compare them. First one is YOLO. YOLO, for my millennial friends, stands for you only look once. So, yep. This is because this model addresses two problems in one. It's object detection and segmentation. It does it in one pass. Hence the name. It's very complex, but I took the open source version as in the form of library. It's maintained by Ultralytics team, very good. And overall, it's a very good example of minimal effort open source model to use. Basically, you just need to pass the data you use, define the hyperparameters, and then it does the thing for you. On top of that, it also provides brilliant debugging tools and plotting. So totally recommend. And the second architecture I took is UNet. This one, I didn't find the proper implementation in PyTorch on the net, so I decided to code it myself. So yeah, UNet is a 10-year-old architecture, which was initially, according to the original paper, it's intended for biomedical imaging and segmentation. So it's really simple. It follows encoder-decoder pattern. So encoder pattern, which is downwards facing, this is feature map extraction, and then the one that goes up, decoder, is upsampling the feature maps, and it also uses the skip connections to use the data from previous layers to incorporate them in upsampling. Yeah, and how I did it, how I implemented it in PyTorch, I essentially took the ready-made components that PyTorch provides, for example, the convolution layer or a max pool layer. You can take that out of the box and just plug it in your architecture, and like the building blocks, like the kids ones, you just plug and play. And thanks to unimaginable flexibility, I had also an option to make it adjustable depth. So if I needed to go one layer further to make the U shape a bit deeper, I did it with just one parameter. Very cool. So in the learning process, there's one thing you have to consider, and this is the loss function, right? So for each type of the machine learning task, you use traditionally you use another loss function. Here are examples of the loss functions I could have used. Binary cross entropy, it is okay, but it will struggle with the unbalanced data, which my data is, unfortunately. Bless you. Distribution focal loss is another function which is also good, and it is used by YOLO model, by the way, but in my case I would need to adapt it somehow for the multi-label problem. So I was dealing with the thought of coding this myself actually when I stumbled across a really old PyTorch forum post which suggested using this loss function, which fitted perfectly. This is exactly what I needed. And you know you're in trouble when you have to code, when you have to like create a code for something, some formula which looks like your cat walked over the keyboard. So I was really happy that PyTorch made my life easier here as well. So check for the loss function. We move to the quality metrics where there is a similar story. I use these four. You may know them, they're quite popular. Precision and recall are the ones that are used widely across different problems. And then intersection over union and dice coefficient are specifically for computer vision. So I did code them myself in a form of like a utility function, which I called in my learning cycle, and then I needed to average it by class. I needed to average it by batch. It was a lot of work. I'm not gonna lie, this was hard for me. But if I would start, if I would just make a Google search at the time, I would explore a bit more and reveal that there is actually a library for this as well. It's called Torch Metrics. It's not provided by PyTorch itself, but it exists in the same ecosystem, so you can just plug and play. It provides all the metrics that you can imagine, especially now. I think a year ago it was a little bit less than that, but now the variety is just unimaginable. So you can choose the metric that you want. You can easily integrate it with your model. And then you can also plot it, and then you have tools to implement custom metrics. So very cool. Really recommend to use it. Yep. And at this point we have the model ready. We have it ready for training, testing, validation, all this stuff. But as a cherry on the top, you can actually take one step further and optimize your model. And this is a secret weapon of AI. Everybody knows it at this point, GPU usage. Just a small note for the lost souls in the audience that, as myself some years ago, didn't understand, okay, why do we use GPUs? Why are they on such a hype? Why can't we have powerful CPUs? Why can't they handle the same tasks? And the answer to this is actually GPUs were created for handling graphics, which are underneath a lot of matrices and mathematical operations on matrices. This is exactly the computer vision problem. CPUs are smart as well, but they are created for completely different problems. If I can make a really simplified metaphor here, in case of CPU, GPU, we don't need the brain, we need the muscle. So we use the GPU. That's it. So returning to PyTorch, it has great support for GPU usage. It also, as I mentioned earlier, you choose where your data is stored and processed. With an easy transfer, you can change that at any point of your pipeline. You can also do multi-GPU processing if you have the privilege of having multiple GPUs. And also a cool feature that I used in my work as well is mixed precision support with the autocast mode, which you can enable also at any point. What it does, it downsizes the precision. So from full precision, which is float 32, it goes to half precision for the operations that allow it, and then it automatically goes back. So what it does, it just makes your loop more efficient. And it's all automatic. Yep. Also forgot to tell, Google actually went a step further, respect for Google. They created their own hardware, which is called now TPUs, so tensor processing units. I don't think for very generic cases you will notice the difference, but still worth to try. I think Google Colab now offers them on a free tier, so feel free to explore. So yeah, at this point I was talking for almost 20 minutes, so I must show you now the ready-to-use model, which is deployed, tested, and monetized. No. The truth is, I actually had some mediocre results for my model, and especially in medical area, you have to pass a very high threshold to your model to be even considered for usage on real data, because the responsibility is so high. But good news is that I know why, and I'm ready to share the lessons that I learned on my journey, so you can utilize them in your use cases. So lesson number 1. This is more on the statistical side, but classless balance, it will mess up your model. Check it in advance, do some plots. A small imbalance is actually okay, and it's a natural case. It occurs frequently, but if you have crazy imbalance, I would suggest techniques like upsampling or undersampling, which can even it out. Lesson number 2 is GPU usage. So I think in the beginner circle, it's a common misconception that you only need GPUs for crazy cases when you need to build ChatGPT from scratch. This is not the truth. You can actually use GPUs for smaller cases, for not so complex cases, and yeah, and the PyTorch has a great support for them, so feel free to explore. And also, I wanted to say that it's not obligatory to possess a GPU physically, so you can just rent it or cloud source it. It's really easy nowadays. Next lesson is address the amount of data that you have in advance. This is a classic one, right? It's an obvious one, but it's the one that hindered me the most. I can't say for classification cases, I can't say the precise number you have to have for each class, but let's say that the absolute minimum, that threshold that I advise you to have is 1K per class, okay? Now, what to do if you don't have as much data is you can consider data augmentation techniques and also transfer learning. These are the techniques that you can use if you want to artificially create more data based on your existing data. And final lesson is make your stuff from scratch. Don't be afraid to go and explore. With PyTorch, you really have all the building blocks and all the instruments to make your own thing. And I think it's very morally rewarding when you don't just use library, but create something yourself that works. It's a beautiful feeling, and I recommend experiencing it to everyone. Yep. So I'm almost done, but there is one last question I need to address. So the selection of AI libraries nowadays on the market, especially for Python, is huge. Why do we use PyTorch? Why is it? What is the advantage of it? And especially when we have its big brother, TensorFlow, right? So I created this quick flowchart that you can follow if you want to decide if you need to use PyTorch or not. So to break it down, if you're not a complete beginner, just started Python yesterday and want to create a neural network, then if you're also okay with writing your own utilities for some parts of the neural nets, next, if you need the flexibility in your architecture, if you like Pythonic way of coding, OOP, something like that, and also finally, and most important, if you need to read and understand academic papers in machine learning and computer vision, use PyTorch. Okay, this is just remember that you need to. We actually had a keynote session this morning from a lady from Hugging Face, if anyone was there. She was talking about all of those open source models that you can use, multimodal models in particular. If you take a look, the majority of them, I would say 90%, are PyTorch first. So this says a lot, right? Yeah, but whatever you choose, whatever technology, whatever library, let me just wish you luck and have fun, and don't be afraid to make your own mistakes and learn from them, and just enjoy the experience. Yep. Happy coding, everyone. Yep. Any questions are welcome.
I have might missed, but which you finally used, YOLO or UNet?
I used both for comparison. They both produced approximately similar results, which were not great. So it didn't make sense to just select best. And also, if I had to choose personally, if you're interested in like which one I liked most, of course I like the one I coded myself best because I had the most flexibility. But YOLO is a great example if you just want to use something great, which has proven efficiency, and just go with it.
Okay. And then the second question about clustering. So from what I understand, you knew your K before, which is 9. That's why you chose probably K-means, because it's the hardest part about K-means is knowing the K.
Yes, exactly. So I knew the number of clusters in advance. I knew the number of classes, right? It's a different thing. Now it will be most about statistics, not about Python, sorry, but I love it as well. So I knew the number of classes in advance, but I also I did experiments, and I think it's a common case when you put K equal to number of classes, it doesn't perform well if your classes are not so distinct. So what worked for me is putting K equals 12. And yes, and I grouped some of the clusters together. So yes. As I said, with unsupervised learning, it's really hard to like expect 100% accuracy, unfortunately. I think we're going to that direction, but we're not there yet.
We might have a bit of time for the last question.
So as far as I understand, you were using k-means for clustering images, and basically that's how you labeled your data set for training.
Yep, I was, just one correction, I was using not the whole images, but crop out sections.
Okay, and maybe do you think that going the long way, manual labeling all those pictures would have brought better results and you would be satisfied with your model compared to unsupervised learning? Maybe the question, were you satisfied with that data set that you created for your training? Were that like, using k-means, did it produce like desirable data set for training? Could it be that like using k-means you got a lot of errors, and by training a data set, not that very good data set, then you produced like a bad model for segmentation? That's my question. Maybe do you think that manual labeling would give very different results?
Yep, thanks for the question. So in my case, k-means is what I went, this is the final algorithm that I stick to, but I also used other algorithms such as dbscan, for example, hdbscan, something like that. And I just were observing which one performs better, and k-means was the closest to truth possible. Now, addressing the question of the manual labor. Imagine one sample has an average of like 9 artifacts on it. Can be of one class, can be of different classes, and you have thousands of the images like that. So it's a lot of work. It's really a lot of work, and I think I would lose the will to do this project as a whole if I would do this manually, sorry. And also, I just wanted to have fun with automating it. I don't think the trade-off between doing this manually and implementing unsupervised learning is towards manual labor is better. I don't think that.
All right. Sadly, there's no more time for additional questions. There are some questions in Discord for you to answer, and thank
Sure.
you.
Thanks.